Okay, is this good? Last call? No last call? Awesome. All right. We'll tackle this. I think we might be able to finish this. I believe I have an osmotic pressure problem. Let me double check if it's one we've done. You can tell me. Have we done this in class? I couldn't remember. Or if you forgot, who cares? I'll do it again. Okay. So, we may or may not have done this in class, but this is a good, very normal example. Should I do a little review of osmotic pressure? Okay, mini review. I'll do that at the top of the page here. We'll get back to the problem in just a moment. Okay, I'll let you copy it down in just a moment. There's really, when you talk about colligative properties, there's two equations. The pi equals IMRT, and the delta T equals IKM. Okay, those are your two main equations. There's two general types of problems. It doesn't matter which one you're talking about. One is just plug and chug. Meaning, what that means is you're given all the variables except one, and you just plug them in and solve for the one we asked for. That's usually, for most people, the simpler type of problem. Okay? The second type involves a little bit more, where we usually ask for one of the following. Mass, molar mass, molecular formula, MOL, molecular formula, or moles, something like that. So we ask for one of those things, and the tricky part is depending on the formula you're looking at, it doesn't have any of those variables in it. So what we want you to do in that case is take these formulas. For the first case, you want to solve for, in the first example, molarity. In the second example, this second formula here, little m, molality. So we want you to solve for one of those and then convert to the asked unit or variable. So you can use dimensional analysis or whatever you need to convert from molarity or molality to what we want. Mass, molar mass, molecular formula. And that's the kind of problem I have here. You'll see, I just used double capital M for molar mass of a protein. And in this case, it's put in water. I know it's an osmotic pressure problem because it has the pi at the end of the problem. So if you see a pi or the words osmosis or osmotic pressure, it has to be this kind of problem. There's no other problem that can involve that variable. So here's a typical problem where I ask you for something that's not in the formula. So it's the second case where we're going to solve, in this case, for molarity, and then we're going to convert from molarity to what they asked for. Okay? So we'll try that. Let me get a different color out. I'm going to scoot this up. So we're going to use pi equals IMRT. And let's just see what we got. T equals 25, and I need to add 273 to that, so it's 298 Kelvin. R, this is like the ideal gas law. We'll give you R on the test. You'll just need to know which one to use. And since the osmotic pressure problem is like the ideal gas problem, we're using this R. Let's see. I, what do you think I is? It's going to be 1. How did you know that? That's correct. Yeah, it's a protein. Anything organic, biological, anything like that will be 1. If it's anything ionic, that means if it has a metal in it, then it'll probably will not be 1. You need to add up the ions. Okay, so I equals 1, and we've got pi is 1.12. Torr, I'll need to convert that though, so let me work on that. Pi equals 1.12 torr. Really, I need this in atmospheres because R is in atmospheres. Is that unusual to have to do a conversion? 760 torr, and we'll give you this conversion if you need it on the back of the exam. And that'll convert you to atmospheres. And let's see. I don't know if I calculated that number per se. I did. Here it is. 1.47 times 10 to the minus 3 atmospheres. Okay. Now, I'm just going to plug in and solve for molarity right now. Let me move this out of the way. Okay, molarity equals pi over IRT, or 1.47 times 10 to the minus 3 atmospheres, divided by 1 for I. R is 0.08206. And T is 298. M turns out to be 6.01 times 10 to the minus 5, and because it's molarity, it's moles per liter, and you could double check the units, and that's exactly what you get. So there's molarity. Now I need to convert to the unit I was asked for, and that's not molarity, I was asked for molar mass. So I want grams per mole. So here's what I'm going to do. I was given in the question, let me just double check here. In the question it said I have I'll change colors here. So here's my conversion part. I was given 1.00 times 10 to the minus 3 grams of the protein. Okay? And when it's dissolved to make 1 milliliter of solution. So it's really a gram per 1 milliliter of solution. So that was given in the question. It says there's 1 gram of the protein dissolved to make 1 milliliter of solution. Now what I'm going to do first, and you'll see why I'm doing this in a moment, I'm going to convert the milliliters to liters. 1,000 milliliters to liters. And then I'm going to use this right there, that molarity, as a conversion. And you'll see why. I'm going to put the liters on the top and 6.01 times 10 to the minus 5 moles. So it's molarity, I just flipped it, and now notice what happens. The liters will cancel. The milliliters cancel. I'm left with grams on the top and moles on the bottom, which is molar mass. And that's exactly what I wanted. And so I just had to do a little manipulation in order to get there. By the way, am I expecting a big or small number for a molar mass of a protein? A big number, a biological entity, usually they're huge molecules, and this turns out to be a very large number, 1.66 times 10 to the 4 grams per mole. Okay, so I got a pretty big number, and there's my molarity. So the second step, plug and chug was really on the top. The second step was conversion. I did that in brown. Any questions? And this will be true for the other colligative property problems as well. All right, let's move that to the side. Let's move on. We busted out chapter 13 already. We're going to move to Q and K and KP. Let's do those next. Okay. So, what you would want to be able to do is determine if something is favorable and determine if there is a shift. Okay, those are two different things not related to each other. If something is favorable, you need to determine that by comparing Q and K. So if Q is larger than K, oh, I got this mixed up. 1 and K, sorry, 1 and K. So K compared to the number 1 tells you if it's favorable. Favorable tells you which side equilibrium sits on. So are the reactants favored? That means there's more reactants at equilibrium, or products favored. So if K is bigger than 1, what's favored? Products, and if K is smaller than 1, then it's reactants. Shift is when you compare Q, sorry I got those mixed up at first, and K. So if Q is bigger than K, which way will it shift? To the left, and if Q is smaller than K, it'll shift to the right. In most cases in our current chapter, in the acid-base chapters, we don't have to do this calculation because on one side there's a 0. Typically there's a 0 on the right. So Q is usually 0 because it's products over reactants, and thus the shift is going to happen to the right Because when Q is 0, K is not going to be 0, even if you don't know what K is. It's going to be a numerical value, 5, 1,000, whatever K is. And that'll mean that if Q is 0, it's going to shift to the right. So often, we have not done that recently. However, in the chapter 14 problems, the chemical equilibrium problems, you need to do this Q and K comparison.
Question?
Yes?
I thought if you had a 0 on reactants, it makes Q infinity more flexures.
Yeah, I was talking about Q on the products. I don't know if I said reactants, but typically in the problems we're doing now, Q will be, there will be a 0 on the product side. Yeah, you're right, though. If Q is a 0 on the reactant side, then essentially Q is infinite, because products over reactants, so shift back to the left. Okay, that's really all I have to say is Q versus K. So you're just looking for one of these key words in the problem, and that tells you what to compare with the other one. Okay? And that's really it. This would be either a concept question, it could be a math question if we give you numbers here for Q, or it could be folded into an equilibrium problem to where like one of the parts, maybe not even related to the other parts, asks you which side is favorable. Or asks you, there's so much of this, which way will it shift? Okay? So you could see it nestled in another problem, but typically these would be a small question relatively. Okay, we also had something on KP. Was there something specific that you wanted to know about KP?
Not really, just like in general.
Just in general? Okay. This formula is the main formula to convert back and forth. We'll give you this formula. Remember, R is the ideal gas law, R, and then T is in Kelvin as normal. Delta N is the difference between the products and the reactants. The number of moles of what state? Gas only. Gas only. So make sure when you find delta N, you're only talking about gases. And the only reason you'd have to use this formula, case 1, we just ask you to convert. So we give you KC, convert to KP, and it'll be a simple calculation problem. Or in the example where we say we give you an equilibrium problem in concentration units, but then we give you a KP. One of those you'll have to switch, either KP to KC, or you have to change all the concentration units to pressure units. So KP must match pressure units, or KC molarity units. If we give you a mismatch, then you need to choose to convert one, and it won't matter which one you convert, unless we specify to give you a specific unit in the end. Okay? Notice also, if delta N is 0, what's this term here on the right-hand side going to be equal to? 1. So if delta N is ever 0, Kc and Kp are equal. So every once in a while on a multiple choice question, you'll see this on the practice exams once in a while, that'll pop up. Where they'll be equal, there's no calculation necessary actually because Kc and Kp are equal. Okay? As far as the ice table goes and all that other stuff, it's a pretty typical problem. However, if you do have a Kp problem, there's a good chance that you'll need to do the quadratic formula. Let me say one more thing about it and write down an ice table for us. Let's say we have A plus B goes to C. Let's say they're all gases. We have I, C, E, this kind of problem here. And let's say this is in units of pressure. So let's say you have 2 ATM, 1 ATM, and 0. And then you'd go, okay, it's going to shift this way, plus X, minus X, minus X, 2 minus X, 1 minus X, and X. Okay, let's say you have some setup like this. This X would be the partial pressure of C. 1 minus X is the partial pressure of B, and 2 minus X is the partial pressure of A. If we wanted the total pressure, how would you find that? Yeah, the total pressure is the partial pressure of A plus the partial pressure of B. Remember, it's just the sum of the total, all the pressures. And in this case, it'd be 2 minus X plus 1 minus X plus X. And you just add these together. That'd be a total of 3 minus X. That would be the total pressure. So in this case, you need to solve for the equilibrium, get X, and then you can get all the partial pressures if you need that. You can get the total pressure if you need that. Okay? So that's a common way to pair a total pressure with an ice table problem. Okay. Okay, I'm going to move on. Oh, yes.
How do you know when to use X and when it's a number in the X table?
On the C line and the E line, if you're solving for equal, she's asking how do you know when you use X in the ice table versus a number. In the C and the E line, it's always going to be X if you're asked to solve for equilibrium partial pressures, okay? Or equilibrium concentrations, or pH. Okay, anything equilibrium, it's always X there. It would be more rare to not have X there. That would be the scenario where it could be in a problem where we give you X and we tell you to find, say, K. And that would be the backwards of the problem, where X is given and we could give that. The most common way to do that, since you asked, this is off the partial pressure problem now. Let's say we gave you an acid, like this. I can't remember if I'm going to do something like this in class. I believe I might. Say I give you something like this, and you're like, oh, okay, ice table, whatever. And then we go all crazy on you, and we give you the pH. pH equals 4.3 or something. You're like, what do I do with that? If we gave you that, we're actually giving you X. Because that would be this value right here, the E line of H3O+. If I write on a different page, pH in this case is 4.30. That's the negative log of H3O+, or concentration of H3O+, equals 10 to the minus 4.30. This is X. So if there's ever a problem, say a weak acid or weak base, and we give you pH, we've just effectively given you X. And then it would depend what we ask for. Oh yeah, I think I am going to do a problem like this. So you'll see in lecture next time how this would play out. But essentially we could ask you for, say, Ka in this example. So it would be the backwards of what you're normally doing. Usually we give you K, you solve for X. This would be the reverse. Okay, let me move on from that. Let's do a Chatelier problem. It'll be, the question is, will this be on the exam? It could be on the exam where we give you X, I guess give you X, and then you have solve. The reason I forgot why I'm doing it in the next lecture, but it's kind of a review practice problem instead of a new material problem. Yeah. Okay, what the heck was I just going to do? Le Chatelier, there we go. That sounds right. Okay. And I came with an example here, I believe, yes. 3Cl2O, that's a gas, plus 10 NH3, that's a gas, goes to 2N2, that's a gas, plus, oh my god, out of room, 3H2O, that's a liquid, plus 6NH4Cl, ammonium chloride, that's a solid. Okay, so there's my reaction. Here, I'm going to do, I forgot who asked this, but I'll do the more difficult of the types of problems. So the more difficult says this has a table, and it says change, and then it will have another column that'll say quantity, and then it'll have another set of columns that'll say effect, effect, and then it'll go like this, increase, decrease, or stay the same. Okay? So in our example here, let's give this a try. I want to add N2, and what does that do to H2O? Oh no, not that one. I want to do, what does that do to N, oh no, that doesn't make sense. NH3 is what I wanted. Okay, so if I add N2, what is that going to do to NH3? Yeah, if I add N2, it'll shift to left and increase the concentration or partial pressure of NH3. So I'm going to put an X in the increase column there. Let's just mess around for a little while. What would this do to K if I add in 2? K is a constant, so that means no change, or stays the same. Remember, no matter how much I add of any reactant or remove a reactant, add a product, whatever, K is not going to change. That's a constant. I'd have to do something like change temperature in order to change K. All right, let's try another one. I'm going to decrease the volume. And I want to know the effect on N2, concentration, or partial pressure. So first, which way will it shift? Yeah, on the left, how many moles of gas do we have? 13, 3 and 10. And on the right, I have how many moles? Just 2. Remember, it's just gas. Don't count the liquid or solid. So it's going to shift to the right side, the side where there's less volume or less moles. And so it'll shift to the right, so N2 will go do what? Well, I have my pen right here. Increase, right? If it shifts to the right. Okay, let's try another one. I'm going to remove NH3. What is that going to do to Q? Nice, I like this question. Okay. Let me go down so you can see. Okay, I remove NH3, which way is it going to shift? Well, you almost don't even need to think about that. If I remove NH3, what's going to happen to Q? It's going to get bigger because NH3 represents the denominator, or the reactants. So, because the reactants are getting smaller, Q is getting bigger. Then you could, if you want, ask which way will it shift? It has to shift left to make Q smaller. It's too big once you add the NH3. Let's see, if I add helium gas, what's going to happen to N2? No change, so stay the same. If you add an inert gas that's not involved in the reaction, or doesn't react with anything like helium or neon, then it's just going to stay the same. Okay? So that's generally, if you can do this sort of stuff, and I would look at several examples in the practice exams, then you should be okay. Okay, nice. We're rolling here. Okay, let's see what we got next. Let's do acid, base, or neutral. Acid, base, or neutral. Let me get a sheet here. So, okay, this one, let's do. There we go. Let's do this. Strontium fluoride. Okay, it's aqueous. What are we going to do? We split it up into its ions, strontium 2 plus and fluorine minus. And you say, okay, what's a conjugate of that? Strontium hydroxide and HF. Okay, strontium hydroxide, what's that? Strong base. So this is neutral. HF is just a normal acid, so this is a normal base. So I have a neutral and a base, I have a base. Okay? Let's try another one. Let's do NH4 IO3. Is that a good one? Okay, yeah, that'll work. All right, so this is NH4 plus and IO3 minus. NH4 comes from ammonia, and this comes from HIO3. Neither of these two are either a strong acid or strong base. Let me write this. Ammonia is just a normal base, so NH4 plus is a normal acid. HIO3 is a normal acid, so this is just a normal base. In that case, we're comparing an acid and a base. We don't know which is stronger. So now you don't have to do any math, but you do have to go over to the table on the back of the exam and write down the constants. So the Kv for ammonia is 1.8 times 10 to the minus 5. The Ka for HIO3 is 1.6 times 10 to the minus 1. Okay, so I got those from the table, which would be on the back of your exam. Okay, is the acid or base stronger? The acid is stronger. So what's stronger over here, acid or base? The acid. Remember, the conjugate is opposite. The conjugate's always opposite. So thus, this must be an acid. Let's just do one more. Sodium iodide. Well, you'd say Na plus I minus. That's from sodium hydroxide and from HI. Sodium hydroxide is strong base, so we've got a neutral. HI is strong acid, so we've got a neutral over here. So this is neutral. If I had you calculate the pH of this compound, what would you do? You would just write down the number 7 because it's neutral, and that's what neutral means, okay? So you shouldn't be doing any math if I ever ask you to calculate the pH of a neutral compound. You should just write down the number 7, okay? All right, let's stop there with that and move on to the next topic. Okay, let's do this. Let's do Lewis acid, Lewis base. Okay. Let's try this first. So let's get a different color. We've got acid here. The base here, water is acting as the base. So this is the conjugate base, Ca is the conjugate base to HA. And then H3O plus is the conjugate, acid to H2O. Okay? So you should be able to label all those just fine. Now let's think in terms of Lewis. In terms of Lewis, there's lone pairs here on the water. So water is an electron pair donor. Okay? So it can donate its electron pair to the H, and that's how it gets the H3O plus. So that's why it's a base, in other words. So Lewis is a little harder to use, but you can still use the same definition on it. Lewis becomes more helpful when you have an example like this. There, something like that. It becomes more helpful here because ammonia is the one with the lone pair, and so it's an electron pair donor. It's donating that electron pair. So this would be called the Lewis base. Okay, because there's no exchange of protons, you have to use this definition. So this is the Lewis acid, this electron pair acceptor. This final compound wouldn't have a name. Okay? So we have a Lewis base and a Lewis acid. So you need to remember that the Lewis acid is electron pair acceptor. So it's easiest to find the Lewis base, typically. The Lewis base is either, if it's not something obvious like the top one, the Lewis base is either like ammonia, or more generally, something with electrons on it. Okay? The Lewis acid often could be transition metal. But if it's not that specific example, then you're looking for something that has a lack of electrons. So in the Lewis structure, a boron would not have any lone pairs on it. But a nitrogen would, an oxygen would, many of those things would. Okay? So that's all you want to do, just be able to identify it. There's Lewis acids and Lewis bases in the top example as well. It's just easier to use our proton donor definitions. Okay, let's move on. The next topic, let's do percent ionization. Okay, there's kind of two ways that you can get a percent ionization problem. One is the pretty typical way. Again, let's say you have HA plus H2O goes to H3O plus and A minus, and you want to find the pH. So you go ice table. Let's say this is just molarity M. Molarity M. Ignore this, 0, 0, minus X, plus X, plus X. Remember, the plus X is on the side with the 0 on it, so it shifts to the right. And you'll get something like that, and you'll say, okay, Ka is x squared over m minus x. And you'll assume x is small, so you get x squared over m equals Ka. And then eventually you'll just say, okay, the square root of both sides, x is the square root of m Ka. Something like that, and this will equal the H3O plus concentration. So you're going along that route, and then you'll finally say pH is the negative log of the H3O plus, or x. That's a pretty typical problem. And then if we wanted to give you that, we could easily tack on a percent ionization onto that. And what we would do is just a simple calculation. And I believe this formula is not given. So this is, I believe, one of those that you'll just need to know. The percent ionization is the x value over the initial concentration. So it would just be that in this case. Whatever you get for x divided by the initial concentration. That would be the simple version. In a long answer question, probably like 2 points, or maybe 3 points. The reverse, and what you might have seen on Mastering Chemistry or the homework somewhere, is if we do the following, where we do something, let's say we give you the percent ionization is 4.2%, say, and then we want to know M. And people kind of get all tweaked out about that. It's basically the entire problem in reverse. So what you might do, or what you would do, from the percent ionization, and we might have to give you one more piece of information, but you have this, like we could give you, we might give you X, say for example the pH. You could find molarity, but you basically are going to go backwards. So you have this formula for percent ionization with X and M, and then you're going to go backwards to find M. And if someone has a specific example, I could do that when we get to our specific questions. But that would be the way a reverse problem would go. So we would give you this number, and then you'd have to find M. So it's the exact opposite of what's in black. Okay, so that's all I'll say about that for now. Definitely, if you have more questions, ask me when we get to our specific part. Okay, let's do, which one is a stronger acid? So structure effects. Okay, in this case, and let me flip over to the reader on where that is. So inspire me to think of problems. This is really on page like 76, 77, right around there. I'll just give you 2 acids. Well, let's do a little summary first. You're looking for 4 effects for acid strength. Okay? The first 2, let me summarize by a rectangle. And this will be our periodic table. Basically, as you go to the right and down on the periodic table, you increase acid strength. And the horizontal line is due to electronegativity effects, and the vertical line, I'll put POL, polarizability or size effects. So to the right and down on the periodic table is increased acidity. So those are 2 of the 4. The other ones are the inductive effect. And basically, instead of usually a hydrogen, you'll see a chlorine or a fluorine. That'll make it a stronger acid. And then the last one, resonance. You're looking for something that would have resonance. So you're typically looking for something with a lot of oxygens, or double bonds, or triple bonds. And that'll more likely have resonance. Ideally, in your head or on paper, you can draw out the resonance structures. But I know that takes time. So if you're in a pinch, you're looking for one of these or a set of these, and it makes you think, okay, there's more likely resonance, that more likely makes it a stronger acid. Those are the 4 effects you're looking for. And so we'll typically give you a set of acids, like H2SO3 and H2SO4. You look at these 2, you're basically saying, and we'll ask you which one's a stronger acid, for example. You look at the 2 and see what the difference is. The main difference is the number of oxygens. And so that tells you, even without doing the Lewis structure, that this one's going to have more resonance in its conjugate base. And because of that, this one's going to be the stronger acid. Which should be what you know, because this is one of our strong acids. Or if we have something like NH3 and H2O, then now the main difference is the atoms, especially when the atom is not carbon or hydrogen. you're looking at the periodic table, oxygen is more to the right, so because of electronegativity, it'll have a more stabilized conjugate base, and this will be the stronger acid. Okay? One that I've had on tests before would be something like this. Let's see. Yeah, I like this one. Okay, that's a good one. And I would say, given this monster molecule, which proton is likely to be lost or donated? So, in other words, which proton is most acidic? This is another way of asking the same question, but now all the protons are on the same molecule. In this case, what you would want to look for is, okay, what's the difference? Well, the protons are in different atoms. So let's see what atoms they're on. Some are on a carbon, some are on oxygen, and some are on a nitrogen. Well, if you look at your periodic table, which one is most to the right? You would say oxygen. So because of electronegativity, the proton on the hydrogen must be the most acidic. So if I had to label this, this would be the first most acidic, the one on the oxygen. Why? Because it's the most to the right on the periodic table. That's why if you have an alcohol, an OH group, that's the one that's the acidic group, because oxygen is the most electronegative. The next most acidic would be this one right here, these hydrogens, because the nitrogen is next. And then the furthest to the left would be carbon. So those hydrogens on the carbons they're not necessarily tied for 3, but they're the worst. So carbon is least likely to donate a proton because it's the least electronegative. Okay? That's another way to see that kind of problem. So make sure you look on practice exams, and I have a lot of these on YouTube. This is most likely, you can see these problems in different places, but typically I put them on a table on the test, and I have you compare 2 molecules and circle the one that's most acidic. Okay, let's try the next area, polyprotic trends and whatevers. Okay. Okay, can you, I think with somebody up here, specify polyprotic trends? What did you mean? Just general concept or something more specific?
Basically, like when you're solving for like H2PO4 and H2SO4, you know how you can skip the first ionization and then the concentration is the same for the second ionization.
All that stuff? Okay, I know what you mean. Okay, so just general, here's what happens. There can be really 2 different types of problems, okay? And if you want to now or later, and if you needed these numbers, we'd have to give it to you on the test, but you can refer, if you have your textbook now or later to page 669, this is just the table. This is how I would generate a question. I just look at this table and pick a molecule off of this table usually, or one that I've heard of otherwise, and let you know what some of the K's are. And so, really the 2 different types of problems you could undergo is if you have, for polyprotic, the 2 different categories would be a strong acid polyprotic or a weak acid polyprotic. So let's split the page in half to take a look at that, okay? And they're slightly different only on the first step. Otherwise, they would be the same. So the only strong acid polyprotic that we know is sulfuric acid. So let me write that one down. H2SO4. And let's say I had like 0.5 molar of that. And then what I would typically ask for is the pH, the concentration maybe of H2SO4 itself after the reaction occurred, the first loss of the proton, concentration, and then the second loss of the proton. So equilibrium concentrations and pH. Okay. In contrast, let me write down a weaker acid. Let's just do oxalic acid. So that's H2C2O4. Let's say this is 0.5 molar as well. Okay. And let's say I also wanted to know pH. I could know the concentration of H2C2O4. I could know or ask for the first loss of the proton. and the second loss of the proton. This would be a pretty typical question. You can see how the questions are really similar in that I'm asking for essentially the same things but for two different molecules. The first step of solving this will be different. The rest of the steps will be identical. Okay? And because for a strong acid, we don't use an ice table. So you will not see an ice table. You'll have a quick, fast first step. For this one, it's going to be a slow solving because we will need an ice table to solve this one. Okay, so let me show you how that would work. Let's get a different color here. Okay, so the first one, because the initial H2SO4 concentration, I'll put 0 there to remind me it's initial, will equal the HSO4 minus concentration at equilibrium and the H3O plus concentration. Meaning all the 0.5 molar is going to react and it will form 0.5 molar of both of those products in the first reaction. So I already know, if I make a little check mark here, I already know this concentration. It's 0.5 molar, this one right there. I know the sulfuric acid concentration at equilibrium would be 0 because it all react away. Initially it was 0.5, but it's all going to be gone. So this one right here would be 0. So I'm already done with that part. I could easily find the pH. It would be the negative log of the H3O plus. Because I already know H3O plus, I don't need an ice table. Again, it's a strong acid, so it's just the negative log of 0.5, whatever that is. Okay? So that would be the pH, so I've already got that. And then the sulfuric acid, or the sulfate ion, that's the one that has just lost 2 protons. You don't even need to do any math here. You would just need to remember that's equal to Ka2. And I would have to give you that number in the problem if I asked you for that concentration. And I believe it's 1.1 times 10 to the minus 2. Yeah. So now I'm done. For this first part of the problem, is that okay? Okay, for the second part, well, that one's done actually. For the one on the right, the weak acid, this is going to be a little bit different now. Here's what's going to be different. I need an ice table. So I would need to write out this whole reaction. C2O4 plus water goes to HC2O4 minus plus H3O plus. So there's the reaction. I need that because I'm generating an ice table now. Okay, I ignore water. I put a 0.5 here, 0 and 0. I shift towards the right, towards the 0, so that's where the plus x is. And so I have 0.5 minus x, x, and x. So then I would have, now I have an ice table. This ice table, all it's helping me do is find the H3O plus concentration, which I had really easily in this other example where I just put a mark that I didn't want to mark there. Okay. So Ka1, which I'd have to give you, it's 5.6 times 10 to the minus 2, is products over reactants, or x squared over 0.5 minus x. I say x is small now. Done. That's gone. And now I'm going to solve for x. And I'll just write it here. Solve for x. And x is going to be equal to a couple important things. First, H3O plus. Second, it's the HC2O4 minus concentration. And so once I find x, if you look, if I check off my list up here, once I find x, I'll have HC2O4 minus. I also will know what 0.5 minus x is, so I'll have this number up here, once I know x. And then pH is easy to find. I'll say pH will be the negative log of the H3O plus, which is just x. So I'll also have pH, check. The only thing I don't have yet is the C2O42 minus concentration. That will be identical to what I did over here at the bottom. The C2O4, because it has just lost 2 protons, no math is necessary, it's just Ka2. And that, in this case, is 5.4 times 10 to the minus 5. And that's molar. So now I have my last concentration. Check. Is that okay? Okay, so make sure you see the difference between these two types of problems. One's a strong acid, the other's weak. So you solve them slightly differently. All this, to get all this right here where my fingers are, is just to determine the H3O plus concentration, which I knew immediately in the strong acid part of the problem on the left. Okay, once you have that, that problem should be okay. Okay, let's see what else we had. Where's my check-off list here? Okay, next. Oh, we finished that chapter. Awesome. Common ion and buffers we'll do together. The common ion, let me start with that, can have really two categories. It can be in a multiple choice problem. So let's say I have HF, and let's say this is 1 molar. And then I add sodium F. And let's say that's 1 molar. Okay. In a multiple choice problem, it would be purely conceptual. So all I would ask is, let's say I had HF initially. First of all, if I had just HF, would the pH be greater than 7 or less than 7? Less than 7 because it's an acid. Okay, now I add sodium fluoride. Sodium fluoride, what is that? Acid, base, or neutral? It'd be a base. Specifically, it's the conjugate base of HF. It's also adding the common ion, which is fluorine. So now I'm adding a base. Should the pH go up or down? And that would be a typical multiple choice question. So I'm adding a common ion in this case. It'll cause the pH to go up. Okay. Now, this also will pair with a buffer problem because I have an acid and its conjugate base. So we could have math involved in this one. But I think I did this one in class. So let me pick another one here for our buffer example. And we'll go through some math for it, just so you can see how it all works. Because as you've probably seen in the practice exams, sometimes a buffer problem can be a long answer problem. Okay, let's say I have HCN. And let's say I have 1 molar of this. And then let's say I have KCN. And let's say I have 2 molar of this. Okay. So the acid, it would have a pH of less than 7. The base would have a pH greater than 7. These are conjugates, so they form a buffer pair. We have the acid and the conjugate base. They're both weak. They both have a molarity that's somewhat similar to each other, so they count as a good buffer. When I add the CN minus, or KCN, to the acid, because I'm adding common ion, the pH again would go up. Okay, so that could be a question in a multi-part long answer problem. Now, there'd be a couple questions I could ask you. First, what's the pH of just this? Or I could ask you, what's the pH of both of these? Or I could ask you just the pH of this one. Now let me ask you, do you want me to just focus on the buffer, or would you like another set of problems with the pH of the individuals? Who wants me to just focus on the buffer? Okay, maybe I should ask it in the negative. Hold on. Put your hands down. Forget you people. Okay. Who wants to do one of these individuals? And tell me which one. So this is an acid. We rated an acid. You want to see me do the conjugate base? Yeah. We haven't seen one of those yet. So I'm going to find the pH of just this one first, and then I'm going to find the pH of the pair. And then I'm going to do something else. And then we'll be done. Okay, there's too many thens. So first, if you needed the pH of just KCN, first you ignore K because it's a spectator ion, so I just CN minus. And what you would do is you go CN minus, write down the general equation for a base. CN minus grabs an acid, or grabs a proton, I mean, and then water loses a proton. So you have an ice table, ice, and then you would say, okay, this was 2 molar. I ignore water, 0 and 0. And this is assuming I'm not mixing with the HCN. I just have this KCN by itself. So that's why there's 0 here. Okay, minus X, just like you've seen before. And then plus X on the side where there's zeros. So now K, what's the subscript? KB equals X squared, both the products over the reactants. I'm going to ignore X, so this will just be X squared over 2. Okay, the problem when you do, sometimes you do a base, is that there's no KB for Cn minus. The only thing you're going to find on the table on the back of the exam is the following. You'll find a Ka for HCN. Let me write that number down. That is 6.2 times 10 to the minus 10. So you'll find a Ka, but you won't find a Kb. In that case, you can find Kb by saying, okay, that's Kw over Ka, because they're conjugates. Kw will be on the back of the exam, 1.0 times 10 to the minus 14. And Ka will be on the back of the exam, 6.2 times 10 to the minus 10. And you can use this to find Kb, to plug into this formula up here. Now, one more thing about that formula up there. You're going to, let's go back to purple. You're going to take this down here, and you're going to say solve for x, okay? And you get a value for x. That will equal the OH minus concentration. Remember, there's OH minus from the ice table, not H3O plus, because it's a base. So what I would do first is find POH, which is a negative log of the OH minus concentration, or negative log of x. And then because pH plus POH equals 14, you know POH, you can solve for pH. You should get a number bigger than 7 because it's a base. Cn minus would be a base. Okay, so that's how you would do a typical base problem. Now, if you add those two together, so you say, let's go back, what did I have? I had 1.0 molar HCN plus a 2 molar KCN. To solve for the pH of this, because it's a buffer, you don't need an ice table, you can use the Henderson-Hassel log. Plus the log of the base over the acid. Or pH equals pKa, which was 6.2 times 10 to the minus 10, or on this table it gives you pKa, so I'll just take that number, it's 9.21. So I had the Ka from before, it's at the top of the page, 6.2 times 10 to the minus 10. If you take the negative log of that, you'll get 9.21. It's also on the table that I'll give you on the exam. Plus the log of the base, 2, over the acid, 1. So you can find the pH of this, it'll be close to the pKa. Okay, that's one type of buffer problem. There's multiple types of buffer problems, I'll just show you one more. Remember that all the ones that you saw or will see in your buffer lab, those could be fair game for an exam as well, especially those pre-lab calculations. Okay, so the other type is now to your buffer, this to that, you add, let's see, and somebody wants to help me, you want acid or base? What's your favorite? Of course acid. So you're going to add an acid. So let's say we add HBr. And let's say we add 0.010 moles of HBr. And the total solution volume doesn't change and it stays at 1.0 liters. Okay? And that's usually pretty typical. We'll give you a volume. Sometimes we'll give you a volume of each separate species and you'd have to sum them up. All right. There's two parts of the buffer. Is this acid going to react with the left side or the right side? The right side, yes, because, yeah, this is an acid and this is a base. So if you add an acid to the buffer, the base part of the buffer will react with it. If I added a base to the buffer, the acid part would react with it. So the opposites like to react. And so we're going to have this kind of reaction, Cn minus plus HBr, and remember, let's write this in a different color. HBr, when I see an acid, I'm really thinking H3O plus. And if you didn't realize this, H3O plus and H plus would be the same. So HBr has an extra H plus, or I'm really thinking H3O plus. So when I write my reaction, what's going on, All right, H3O plus, and remember this represents HBr. The Cn minus will react to form HCN, HCN, and the H3O plus will lose a proton. I wrote a single-headed arrow. Does anybody know why? I have a strong acid HBr, and that drives the reaction 100% to the right. So which side is the favored side, products or reactants? Definitely the products. Does that mean K for this reaction will be large or small? Very large, okay? So let me write down the numbers we have right now. The HCN is 1 molar, but because there's 1 liter, that'd also be 1 mole. And this is 0.010 moles. The HCN, oh no, this is 2, sorry, that was 2. This is 1, and we ignore water. So I remember I did a 0 on the unfavored side, or this is going 100% forward. So I'm going to subtract the limiting reactant, or the smaller number, from both sides, and add it to the products. And sum this up, this will be 1.99, this will be 0, and this will be 1.01. Now if I had to find the pH, and we call this a stoichiometric table, whenever you add something to a buffer, add something strong, whether a strong acid or strong base, you will do one of these stoichiometric tables. Okay, so the pH is pK plus the log of the base over the acid. pKa was 9.21. The log of the base, that's 1.99. And the acid is 1.01. And whatever that is will be the new pH of the buffer. Okay, so that's a pretty typical long answer buffer problem. Cool. I think I'll pause right there. Anybody who wants to take off, get the heck out of here. Go practice running so you can beat me next time on the 5K. Some of you are too slow, except for one fool over there. And then the rest of you, stick around. We'll do specific questions in just a moment. This is hustle.